Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our second lecture covering material from Chapter 5. Please realize that this is not equivalent to our actual lecture where we will discuss and practice the material in much more detail. In other words, come to class. This lecture begins with a heating curve for water. If we start at the origin, we are at a temperature below zero and we're adding heat. Imagine a block of ice in a stock pot on your stove with the heat on a high setting. The temperature of the block of ice will increase until we reach the melting point. At this point, the ice block starts to melt and the temperature remains constant until only water exists. The same happens at the boiling point at 100 degrees Celsius for water. You can perform an experiment at your home using a pot of water. Heat it to boiling and measure the temperature, and then turn your stove up to 11. You would expect the temperature to increase, but it won't. The phase change phenomena can be explained in terms of energy. Temperature is average kinetic energy, so as our ice or water is heated, the molecules will move more rapidly, but during the phase change, we do not see a change in temperature. This can be explained with potential energy. The molecules are moving further apart from each other, which is an increase in potential energy on the molecular level. We calculated heat in the previous lesson using Q equals mc delta T. During a phase change, there is no change in temperature, so we cannot use this formula. For melting, we will use the formula Q equals mass times the heat of fusion in joules per gram. Fusion means melting. The other phase change is determined using Q equals mass times heat of vaporization. Heat of fusion and heat of vaporization values are provided. You don't have to memorize them. Notice in the upper right sketch that we have a cooling curve. The temperature is decreasing in this diagram. The phase change from water to ice is simply called freezing, and the magnitude of energy is the same as fusion or melting, but now the energy is being released. We can use the heat of fusion value, but we'll have to change the sign. The same applies for condensation, which is the process of going from gas to liquid. The heat of fusion and vaporization for water are given on this slide and will be provided on any exam. An example problem is provided at the bottom of the slide. You want to draw the heating curve prior to attempting any of these problems because it will provide a roadmap for your calculations. This is the diagram that you will draw prior to doing any calculations. It is expected that you would know the freezing and boiling point for water, which are 0 and 100 degrees Celsius respectively. If the substance is not water, the melting and boiling temperatures will be provided. It is good practice to write these on the y-axis. For this problem, we will start at the cursor, so right around here, and end at the gas phase at 100 degrees. This is 100 degrees up here on the y-axis, and the gas phase will be right here. This problem will require two calculations. We will use Q equals mc delta T to warm from 40 to 100, this section, in the liquid state, and then Q equals mass times the heat of vaporization for the phase change from liquid to gas at 100. That's this section here. We will sum the two values to get the total heat required. This is the solution to the previous problem. You should try this on your own by starting with the heating curve and mapping out your start and stop locations. This is another problem for you to try. The heating curve is provided, but be able to draw this in case it's not provided on the exam. Since the material is water, we know the freezing and boiling temperatures. The other constants are provided and will be provided on your exam. Pause the video and try this, as a detailed answer is on the next slide. This problem required 3 separate calculations. Enthalpy diagrams, or potential energy diagrams, represent a reaction in terms of energy on the y-axis. Instead of writing reactants, arrow, products on one line, we scale the energy or the enthalpy of the reactants and products. In this example, the reactants have more energy than the products, therefore energy must have been released in the process. This is an exothermic reaction. Notice this diagram shows products at a higher enthalpy or energy than the reactants. Therefore, the reaction must have gained energy, or we can say this is an endothermic reaction. As we move forward, you will see delta H written in a few different formats. Delta H reaction is the heat change for a reaction written as a balanced equation. These values are typically in kilojoules, and the sign dictates the direction of heat flow. A negative value represents an exothermic reaction. Standard molar enthalpy and enthalpy of formation are written on a per mole basis, so the units will be kilojoules per mole. We will describe these in more detail moving forward. This reaction has a delta H that is negative, meaning that the reaction is exothermic. We can write the energy value into the equation. Since it's exothermic, that means heat is given off. So we can write the value on the product side of the reaction because the reaction produces heat. Since it is on the product side, we know that the reaction is exothermic and the negative sign is no longer necessary. There are now factors relating quantity of reactants or products and energy based on the balanced equation. We will wrap up this mini lecture with some homework. This reaction has a change in enthalpy of 802 kilojoules, and the sign is negative, meaning that the reaction is exothermic. You can write the energy amount into the reaction, and if you need help, just review the last slide as the reaction is the same. To solve the problem, you will have to convert 128.5 grams of methane to moles of methane, and then use reaction stoichiometry to convert to kilojoules of energy. You should get 6,424 kilojoules of energy released for your answer. Thanks for watching. Please give this video a thumbs up and subscribe if you would like to see more mini lectures on the Professor DuBois channel.